In 2024, a company called Versus AI entered a code-breaking challenge against OpenAI's o1 preview. Their system, Genius, solved it 140 times faster and 5,260 times cheaper. Against DeepSeek R1, Genius achieved a perfect 100% success rate where DeepSeek managed 45% while running 300 times faster and 800 times cheaper. Those numbers should not be possible. OpenAI's o1 preview is backed by one of the largest AI compute investments in history. DeepSeek R1 is a strong reasoning model trained at massive scale. Versus is a startup with a research team you can fit in a conference room. So either the benchmarks are wrong, or something about the way we build AI is structurally broken. I think it is the second one. And the evidence goes beyond a single benchmark. We are 10 years into the deep learning era, and the consensus is starting to crack. Generative AI can produce a photorealistic astronaut riding a unicorn in the style of Togashi. It can write a passable essay on Hegel. It can generate code, translate languages, and summarize documents at speeds no human can match. But it cannot reliably count the number of R's in the word strawberry. It cannot draw a full glass of wine without the liquid defying gravity. It cannot play a board game that a 10-year-old handles without thinking. These are not bugs. They are symptoms of a structural ceiling. The current paradigm is simple: intelligence emerges from scale. More parameters, more data, more compute. This produced GPT-3, GPT-4, and the wave of trillion-parameter models that followed. Each generation was bigger, and each generation was better. The scaling curves were smooth and upward pointing, and for a while it looked like the only question was how much compute you could afford. That story is changing. To quote Sundar Pichai, the low-hanging fruit is gone. Picture a graph. The x-axis is model scale, each tick mark is a doubling of parameters. The y-axis shows two lines. One is capability gain, how much better each new model is at the tasks we care about. The other is cost, how much it takes to train the model. Early in the curve, the capability line rises steeply and the cost line is manageable. But the lines are crossing. The capability gain per doubling is shrinking while the cost per doubling is holding steady or growing. The return on investment is declining with each generation. The scaling curves are flattening. Each doubling of parameters produces smaller improvements. The cost per marginal capability gain is rising fast. And the hard limitations, the inability to reason causally, to generalize from single examples, to adapt to environmental changes without retraining, remain untouched no matter how many parameters you add. Consider the economics. The cost of training frontier models has risen sharply with each generation. Each successive model delivers a smaller marginal improvement for a larger absolute investment. The result is a diminishing returns curve that looks exactly like what happens in any system that scales the wrong variable. If you are building a car, and the car is slow, you can put a bigger engine in it. The first upgrade helps a lot. The second helps less. The third helps even less. At some point you realize the problem is not the engine. The problem is the weight, the drag, the transmission, or the road. Scaling the engine past a certain point is not just inefficient, it is the wrong intervention. Deep learning is scaling the engine. The Versus results suggest the problem is the road. And if the problem is the road, the solution is not a bigger engine. The solution is a different kind of vehicle, one designed for the terrain. This is not just an academic debate. The Iris Swarm API was built from the same structural insight. On the 1251 task Harvey legal agent benchmark, commodity models achieved a 17.75% strict all-pass rate through architectural coordination at $1.30 per task versus $50.90 for previous approaches. The models did not change. The coordination did. That is the difference between scaling the engine and fixing the road. The failures reveal the shape of the wall. When an image generator draws a person with 6 fingers, it is because the model learns statistical correlations between pixel patches. It knows that hands have fingers, but it does not know that hands have exactly 5 fingers. Arranged in a specific spatial relationship. It has no model of hands. It has a pattern of pixels that co-occur with the word hand. When a language model confidently states a false fact, citing a paper that does not exist, attributing a quote to the wrong person, it is because the model learns sequences of tokens that are statistically likely. It has no model of truth. It has a pattern of words that co-occur with other words that co-occur with plausible-sounding citations. When a DeepRL agent trained on one Atari game is placed in a slightly modified version of the same game, different colors, slightly different physics, its performance collapses. It learned a policy for specific pixel patterns, not a model of the game's mechanics. These are not separate bugs. They are the same bug, the absence of a causal model. The system knows what usually co-occurs with what. It does not know what causes what. The distinction between correlation and causation is not academic here. It is the engineering bottleneck. A system that knows correlations can interpolate, it can produce outputs that are statistically plausible given inputs similar to its training data. A system that knows causes can extrapolate, it can predict what will happen in situations it has never encountered, because it understands the mechanisms that produce outcomes. Interpolation works within the training distribution. Extrapolation works outside it. And every real-world deployment involves situations outside the training distribution. This is not a temporary plateau. It is a structural wall. And the reason it is structural is that the paradigm itself, learning statistical patterns from massive datasets via gradient descent, is missing something that intelligence requires. We are going to spend the next 2.5 hours understanding exactly what it is missing, where the alternative comes from, and why a 1.6 million parameter system can. Outperform models with approximately 400 times more parameters. The roadmap: first, we will identify what intelligence actually requires that pattern matching cannot provide. Then we will learn the free energy principle, a theory from physics and neuroscience that describes how all self-organizing systems, from single cells to human brains, build and maintain models of their world. Then we will turn that theory into engineering through active inference. Then we will walk through AXIOM, a complete cognitive architecture that implements active inference and beats state-of-the-art DeepRL on real benchmarks. And finally, we will see why the structural insight behind AXIOM, that coordination matters more than scale, shows up independently in systems like the Iris Swarm API, and what that convergence tells us about the future of AI. Deep learning does something specific. If we are precise about what it does and does not do, the alternative becomes obvious. A deep neural network learns a mapping. You give it an input, a sequence of tokens, a grid of pixels, a set of features, and it produces an output. Internally, it adjusts millions or billions of parameters via backpropagation to minimize a loss function. The parameters encode statistical regularities in the training data. After enough examples, the network can recognize a cat, complete a sentence, or classify a tumor. This is pattern recognition. And pattern recognition is genuinely useful. But pattern recognition is not understanding. It is not even close. Consider what happens when a deep learning model encounters something it has never seen before. Not something slightly different, something genuinely novel. A new game rule. A changed physical law. A color swap on objects it has already learned to classify. The model fails. Not gracefully, catastrophically. It has no mechanism for saying I don't know. It has no mechanism for testing a hypothesis about why the new situation differs from the old one. It has no mechanism for updating a single belief while preserving everything else it has learned. Its only option is to retrain on new data that includes the novel situation, which, means revisiting the entire loss landscape from a cold start. This brittleness is not an accident. It is a consequence of how the system represents knowledge. A neural network stores knowledge implicitly, distributed across billions of parameters in ways that no human can inspect or decompose. You cannot point to a specific weight and say this is where the network knows that red balls bounce. The knowledge is entangled, holographic, and opaque. Here is what that means in practice. Suppose you train a network to classify objects in images: cats, dogs, cars, trees. It does well. Now you want to add a new category: birds. You fine-tune the network on bird images. The network learns to recognize birds. But now it has partially forgotten what cats look like. The weights that encoded cat features have been overwritten by the gradient updates for birds. This is catastrophic forgetting, and it remains an open problem after decades of research. Here is a toy example that illustrates the problem. A network starts at 93% accuracy on cats and 90% on dogs. You fine-tune on 2,000 bird images. Birds rise to 88%, the network learns birds. But cats drop to 61% and dogs to 58%. The network did not delete its knowledge of cats. It shifted the representational space. The weights that encoded cat features were pulled toward bird features by the gradient, and the old boundaries dissolved. The reason catastrophic forgetting persists is that the network has no separation between what it knows about cats and what it knows about birds. The knowledge is smeared across all the parameters. Updating one thing risks breaking another. Every fine-tuning step is a gamble. Now consider what intelligence actually does. Not human intelligence specifically, any system that we would call genuinely intelligent. It maintains a model of the world. Not an implicit one frozen in weights, but an explicit one it can query, test, and update. It knows what it believes, how confident it is, and what evidence supports each belief. A chess player does not memorize every possible board position. They maintain a model of the game: pieces have roles, positions have values, and the consequence of each move can be computed from the current state. When they see a new position they have never encountered, they do not panic. They apply the model. An intelligent system predicts. Given its current model, it can generate expectations about what will happen next. If I drop this ball, it will fall. If I push this lever, the door will open. If I move this piece, my opponent will respond in one of three ways. These predictions are not statistical averages, they are causal. This happens because of that. It tests. When a prediction fails, the system does not retrain from scratch. It locates the specific belief that produced the wrong prediction and updates that belief while leaving everything else intact. The ball did not fall, it floated. Update: this object is lighter than I expected. Everything else I know about gravity, about balls, about this room, remains intact. The update is surgical, not catastrophic. It acts with purpose. It does not wait for a prompt. It has goals, states of the world it prefers, and it selects actions that move the world toward those states. When the world resists, it revises its approach. When the world surprises it, it investigates. And it tracks uncertainty. Not every belief is held with the same confidence. A genuinely intelligent system knows what it knows and what it does not know. It can say, I am 90% sure the ball is here, but I could be wrong. This uncertainty drives behavior, the system investigates where it is. Least certain, because that is where the highest value information is. Here is what uncertainty tracking looks like in practice. Imagine you are a doctor examining a patient with chest pain. You have three hypotheses: heart attack, acid reflux, or muscle strain. Your initial uncertainty is spread across all three, maybe 40% heart attack, 35% acid reflux, 25% muscle strain. You order an ECG. The results are normal. Now heart attack drops to 10%. Acid reflux rises to 55%. Muscle strain rises to 35%. Each piece of evidence reshapes the distribution. The uncertainty is not gone, it has moved. And the next test you order depends on where the uncertainty is now concentrated. If acid reflux and muscle strain are neck and neck, you might order a test that specifically distinguishes between them. You direct your investigation toward the boundary where your uncertainty is highest. A deep learning classifier does not do this. It outputs a single label acid reflux with a confidence score. But that confidence score is not calibrated uncertainty. It is a softmax output that correlates loosely with accuracy. The system cannot say, I need more information to distinguish between these two hypotheses, because it does not maintain hypotheses. It makes a single forward pass and produces a single answer. None of these properties emerge from gradient descent over large datasets. You can scale a pattern matcher to 1 trillion parameters and it will still not have goals. It will still not test hypotheses. It will still not update a single belief without risking the collapse of its entire learned representation. This is not a criticism of deep learning. Deep learning does what it was designed to do, find statistical patterns in large datasets. The problem is that we have been asking it to do something it was not designed for. We have been asking pattern recognition to substitute for understanding. The IRI Swarm API starts from the same recognition. When you need to reason over hundreds of long documents, legal filings, financial reports, compliance records, you cannot just stuff them into a bigger context window and hope the model figures it out. The context window degrades. Attention decays. Facts on page 3 get treated differently from the same facts on page 97. Research on the lost in the middle problem has shown that LLM accuracy on retrieval tasks drops when the target information is buried in the middle of the context rather than near the beginning or. End. The IRI Swarm API structures coordination instead. Picture a shared workspace, a blackboard, at the center. Around it, specialized extraction agents, each assigned to a bounded subset of documents. They read, extract typed observations, and write them to the blackboard. The blackboard accumulates structured state. The system converges on understanding through iteration, not through scale. Each extraction worker processes a bounded set of documents short enough that the model never loses attention. The results are typed, provenance tracked entries on the blackboard. The system builds understanding in layers rather than trying to hold everything at once. Architecture, not parameters. So if pattern recognition is not understanding, what is? Where does the alternative come from? If this level of analysis is useful, where we strip a problem down to its structural limits before building back up, subscribe and like so you do not miss the rest. We are about to derive the answer from physics. It comes from an unexpected place. Not from computer science. Not from machine learning. Not from the optimization literature. From physics. Specifically, from a neuroscientist who asked the question that everyone else was too busy building bigger networks to ask. In the 1990s and 2000s, a neuroscientist named Carl Friston was trying to answer a deceptively simple question: what does the brain do? Not what does it compute. Not which regions light up during which tasks. The question was more basic: what is the single objective that unifies everything the brain does: perception, action, learning, memory, planning, dreaming? This is not a trivial question. The brain does many things, and they look different from the outside. Seeing a face, speaking. A sentence, planning a route, dreaming about flying, these seem like separate functions. Friston wanted to know if there was one objective underneath all of them. The answer he arrived at has become one of the most debated and productive frameworks in neuroscience. It is called the free energy principle. Not everyone agrees with it. Some neuroscientists think it is too broad to be falsifiable. Others think it is the most productive unifying framework the field has seen. What is not debated is that the framework has generated a stream of concrete, testable predictions and engineering implementations. Whether it is ultimately correct in some deep philosophical sense matters less than whether it is useful. And it is. The core idea is this: every self-organizing system survives by minimizing surprise. Not emotional surprise. Thermodynamic surprise. The precise gap between what the system expects to sense and what it actually senses. This gap has a name, prediction error, and it has a precise mathematical form. The quantity the system works to minimize is called variational free energy, which is an upper bound on the true surprise. The name free energy comes from statistical physics, not from energy generation. In physics, free energy measures how far a system is from equilibrium. A system at equilibrium is in its most probable state. It has found the lowest energy configuration consistent with its constraints. A system far from equilibrium is in an improbable state. It is surprised. Why is this called free energy? In thermodynamics, the free energy is the portion of a system's total energy that is available to do work, the energy that is free to drive change. When a system has high free energy, it has energy available to drive transitions. When free energy reaches zero, the system is at equilibrium, no more transitions are possible. The variational free energy in the brain works the same way. It measures how far the brain's model of the world is from the world's actual state. When the gap is large, the system has free energy available to drive belief updates or actions. When the gap reaches zero, the model matches reality perfectly, equilibrium. The intuition comes first. The equation will follow once the intuition is solid. Think about a fish. Picture this visually. A fish suspended in clear water. Around it, a thin envelope, the range of sensory states it expects. Water pressure, dissolved oxygen, fluid resistance. These are the fish's expected sensory inputs. The envelope is its model. As long as the fish stays inside the envelope, everything is fine. Now take the fish out of the water. Every sensory channel screams mismatch. The pressure is wrong. The chemistry is wrong. The resistance is wrong. The fish's internal model predicted water, and reality delivered air. The gap between prediction and sensation, the free energy, is enormous. The fish has one option: act. Flop. Toward the water. Reduce the gap. Drive reality back toward the state the model predicts. If the fish cannot reduce this gap, it dies. This is not metaphorical. Sustained high free energy is not just uncomfortable. For a biological system, it is incompatible with the thermodynamic conditions required for survival. The fish exists as a self-organizing system only because it occupies a narrow band of sensory states. Falling outside that band long enough means dissolution. This applies at every scale of biology. And the consistency across scales is what makes it a principle, not just an observation about fish. A bacterium swims up a sugar gradient. Its internal model, encoded in chemical receptors on its membrane, predicts that higher sugar concentrations mean better conditions. When the gradient reverses, the bacterium's prediction error rises. It tumbles, reorients, and swims in a new direction. The bacterium does not have a brain. It does not have neurons. But it minimizes prediction error. It survives by keeping its sensory states within a predicted range. A single cell maintains a pH balance. Drift the pH too far in either direction and the proteins that hold the cell together denature. The cell's internal model predicts a specific chemical environment. Enzymes and ion channels work continuously to keep the actual environment matched to the prediction. If they fail, the cell dies. A body maintains a core temperature of 37 degrees Celsius. When external temperature drops, the body shivers, generating heat to bring reality back into alignment with the model. When temperature rises, the body sweats, cooling to reduce the gap. The thermostat is an internal model with a set point, and the body's actions. serve to minimize deviation from that set point. A brain maintains a predictive model of its environment. When that model fails catastrophically, when the world becomes permanently unpredictable, the organism breaks down. Biological systems lose coherence when their regulatory variables leave viable ranges for long enough. The free energy principle proposes a unifying account of all of these examples. It is one of the most debated frameworks in neuroscience. Not everyone agrees it is correct, but it has been productively applied across neuroscience, biology, and now AI. The claim, every system that persists over time does so because it has found a way to keep its sensory states within a predicted range. The mechanism is always the same: build a model, generate predictions, compare to reality, reduce the gap. This applies to non-biological systems too. The Iris Swarm API maintains a model of its document set, the blackboard. The blackboard starts empty. As extraction workers process documents, they write typed observations. Each observation reduces the gap between the blackboard's representation and the actual content of the documents. When the supervisor identifies areas where the blackboard's model is thin, where the system is still surprised by queries it cannot answer, it dispatches follow-up workers to fill those gaps. The system converges toward a state where every important fact in the document set has a corresponding entry in the blackboard. That is its equilibrium. Sustained gaps in understanding are the document-level equivalent of the fish flopping on the dock. This is a radically different starting point from deep learning. Deep learning starts with data and optimizes a loss function. The free energy principle starts with survival and derives everything else. Now, and this is where it gets interesting, there are exactly two ways to reduce that gap. Two and only two. The first way is to change your mind. You expected the step to be there, but it was not. Your foot lands on air. Your model predicted solid ground. Reality said otherwise. You have a prediction error. The fix: update the model. The step is not there. Adjust. Now your model matches reality, and the prediction error drops to zero. This is perception. Not perception in the everyday sense of seeing or hearing. Perception in the technical sense, revising your internal beliefs about the world so they better match what your senses report. Every time you recognize a face, parse a sentence, or realize that the shadow in the corner is a coat rack and not a person, you are performing this operation. Updating beliefs to reduce prediction error. Consider a concrete example. You walk into a dark room. Your model predicts, empty room, nothing dangerous. Then you hear a sound, a creak. Prediction error. Your model did not predict that sound. You revise: maybe someone is in the room, or maybe the house is settling. Your updated model now predicts that. Creaking sounds are possible. If the next creak matches this prediction, your free energy drops. You have resolved the surprise. But notice, you did not change the room. You changed your model of the room. The room still creaks. You just stopped being surprised by it. The second way is to change the world. You are cold. Your model predicts that your body should be warm. Your senses report that you are losing heat. The prediction error is rising. You could update your model, learn to predict that you will be cold. But that will not help you survive. Your body still needs warmth. Instead, you act. You put on a jacket. You move to a warmer room. You build a fire. You change reality so that your senses start reporting what your model expects. This is action. Not action as a separate system from perception. Action is the other face of the same coin. Both perception and action serve one master: minimize the gap between expectation and reality. Here is a subtlety that matters: the system must choose which response to use, and the choice depends on which beliefs are negotiable. When the fish is out of water, updating its model, learning to expect air, does not help. The fish's model of where it should be is a preference, not a hypothesis. The fish does not adjust its expectation. It acts. It flops. When the chess player discovers their opponent has a new strategy, moving a piece randomly does not help. The player needs to update their model of the opponent's strategy. Only then can they plan an effective response. The distinction shows. Up in medicine. A patient arrives with a fever. The doctor has two options. Option 1, treat the fever, give antipyretics, bring the temperature down. That is action. It changes the world to match the model's preference for normal body temperature. Option 2, diagnose the fever, run blood tests, check for infection, update the model of what is causing the symptoms. That is perception. The right choice depends on which belief is negotiable. If the patient has a dangerously high fever, you act first, bring the temperature down before the brain is damaged. If the fever is moderate and the cause is unknown, you perceive first, diagnose before you treat. Treating the wrong cause is worse than not treating at all. The same logic applies in engineering. A bridge sensor reports unexpected vibration. The engineer can reinforce the bridge immediately, or investigate whether the vibration is caused by wind, traffic, or structural fatigue. The right response depends on how confident the engineer is in the cause. High confidence in a known failure mode? Act. Low confidence in an unfamiliar signal? Investigate. This is the computational sophistication that the free energy principle formalizes. The choice between perception and action is not hard-coded. It is determined by the precision of the beliefs involved, how confident the system is in its model versus how confident it is in its preferences. High precision on preferences, low precision on the model, act. High precision on the model, low precision on what is happening, perceive. The feedback loop is continuous and aggressive. Every moment, the system is either changing its mind or changing the world. Or both, to keep the prediction error as low as possible. Here is why this matters for AI. Most mainstream deep learning systems do only one of these, or do both without an explicit inspectable causal model connecting them. A neural network trained via supervised learning does only perception, it updates its parameters to match training data, and then it stops. It never acts on the world. It receives a prompt, produces a response, and waits for the next prompt. It is entirely reactive. A model-free reinforcement learning agent, the class that dominates the benchmarks, the DQNs and PPOs, does both, technically. It updates a policy and takes actions. But its actions are selected to maximize a reward signal, not to reduce prediction error about a world model. It does not predict consequences through an explicit causal model. It memorizes which actions historically led to reward in which states. Model-based RL systems do maintain a learned world model, and they are closer to the active inference paradigm, but the model is typically a black box neural network, not an inspectable causal structure. The difference is the same as the difference between a child who understands that the stove is hot and a child who has learned. To avoid the stove without knowing why. Both stay safe. Only one can reason about new situations involving heat. An active inference agent does both, naturally, and in the same loop. It builds a generative model of the world. It uses that model to predict sensory data. When predictions fail, it updates the model, perception. When the model predicts a preferred state, the agent acts to bring reality in line, action. Perception and action are unified under one objective: minimize free energy. This dual mechanism is the engine of all adaptive behavior. The thermostat adjusts the heating to match a set point. The immune system modifies its antibody repertoire to match new threats. The brain updates its model when it is wrong, and moves the body when the model is right but the world is not. The IRE Swarm API uses both mechanisms. During extraction, the system does perception, it reads documents and updates its model, the blackboard. When the supervisor reviews the blackboard and identifies gaps, it does action, it dispatches new workers to gather the specific information needed to close those gaps. The extraction synthesis loop alternates between model updating and world acting until the blackboard converges. Just like the thermostat, the system has a set point, a blackboard that can answer every query about the document set. It alternates between perception and action until it reaches that set point. That covers the two mechanisms. But to turn them into an engineering framework, we need to formalize them. We need mathematics. To turn this from philosophy into engineering, we need mathematics that an algorithm can compute. The formalization rests on one key idea: beliefs are not single values. They are probability distributions. When a human says, "I think the ball is somewhere near the left side of the screen," that belief is not a point. It is a spread. There is a central estimate, the most likely position, and there is uncertainty around it. Maybe the ball is at x coordinate 30, but it could be 28 or 32. Probably not 5. Almost certainly not 150. The mathematical object that captures this is a probability distribution. And the workhorse distribution for most of scientific modeling is the Gaussian, the bell curve. A Gaussian is defined by two numbers: the mean, the center, the best guess, and the variance, the width, the uncertainty. A narrow Gaussian means high confidence: I am nearly certain the ball is at position 30. A wide Gaussian means low confidence: the ball is probably somewhere between 10 and 50, but I am not sure. There is a third number that sometimes appears, the precision, which is the inverse of the variance. High precision means high confidence. Low precision means low confidence. Precision will matter later when we talk about how AXIOM weights evidence, so file it away. This is the native language of any system that has to make decisions based on incomplete information, which is every real system. Now, suppose the world is generated by multiple overlapping causes. The screen does not contain one object, it contains several. Each pixel could be explained by different objects. The distribution of pixel colors is not a single Gaussian. It is a mixture, a sum of Gaussians, each representing a different hypothesis about what is producing the data in that region. This is a Gaussian. Mixture model. And it will turn out to be the foundation of AXIOM's perception. A Gaussian mixture model works like this. Suppose you have data points scattered across a plane. Some cluster in the top left. Others cluster in the bottom right. A single Gaussian cannot explain both clusters. But two Gaussians can, one centered on each cluster, each with its own width. The model learns three things for each component: where its center is, the mean, how wide it is, the variance, and how much of the data it explains, the mixing weight. A component that explains 60% of the data has a mixing weight of 0.6. A component that explains 5% has a weight of 0.05. The weights must sum to 1. The mixture accounts for all of the data, collectively. For each data point, the model asks, which component is most likely to have generated this? The answer is a soft assignment: not this point belongs to cluster A, but this point is 70% likely from cluster A and 30% likely from cluster B. The softness matters because it preserves uncertainty. The model does not commit to a hard boundary until the evidence is overwhelming. Before we get to free energy, we need three Bayesian concepts that the math depends on. The prior is what the system believes before seeing any data. It is the default expectation. Before I look at the game screen, I believe objects are probably scattered randomly. The prior encodes everything the system knew before the current observation. The likelihood is how probable the observed data is under a specific hypothesis. If there is a red ball at position 30, 50, how likely is it that these specific pixels would look the way they do? High likelihood means the hypothesis explains the data well. Low likelihood means the hypothesis does not match what the senses report. The posterior is what the system believes after seeing the data. It combines the prior and the likelihood through Bayes' rule: posterior equals the likelihood times the prior, divided by the evidence. The posterior is the updated belief, what the system should believe now, given both its prior knowledge and the new data. In exact Bayesian inference, you compute the posterior directly. But in complex systems with many hidden variables, exact computation is intractable. The integral in the denominator of Bayes' rule involves summing over all possible states of the world. Variational inference sidesteps this by finding an approximate posterior. That is close enough. Free energy is the tool that measures close enough. Now the free energy math. The system maintains a set of beliefs, probability distributions over hidden states of the world. Call these beliefs Q. The world produces sensory data, call it Y. The system has a generative model, a mathematical description of how hidden states produce sensory data. Call this P, Y, S, the joint probability of observations Y in hidden states S. The variational free energy F is defined as F of Q equals the expected value under Q of negative log P of Y given S, plus the KL divergence from Q of S to P of S. In words, the first term is the prediction mismatch, how badly the current beliefs explain the observed data. The second term is the belief movement, how far the current beliefs have drifted from the prior. This decomposes into a simpler statement, F equals complexity minus accuracy. The loop is, reduce mismatch while paying only the smallest necessary belief movement. Let me break down both terms because they do a lot of work. Complexity is the KL divergence between the current beliefs QS and the prior beliefs PS. How much has the system's mind changed from its default? High complexity means the beliefs have drifted far from the prior, which the system penalizes because extreme updates are usually wrong. Think of it this way. Your default belief is that the weather is mild. You look outside and see dark clouds. You update, it might rain. That is a small KL divergence, your beliefs moved a little from the prior. Now suppose you look outside and see the sky is purple with green streaks. You update, something very unusual is happening. That is a large KL divergence, your beliefs moved far from the prior. The system penalizes this large update, because in the absence of extraordinary evidence, the most boring explanation is usually the right one. Accuracy is how well the beliefs explain the observed data. High accuracy means the model's predictions. Match what the senses report. If you believe it will rain and it does rain, your accuracy is high. If you believe it will rain and the sun is shining, your accuracy is low. Minimizing free energy means, fit the data as well as possible, maximize accuracy, while keeping the beliefs as close to the prior as possible, minimize complexity. This is the same objective as maximizing the evidence lower bound, or ELBO, in variational inference. The math is identical. If you have seen ELBO in a machine learning paper, you have already seen free energy just by another name. This trade-off is the heart of principled inference. A model that perfectly fits the data but requires wild, extreme beliefs is probably overfitting. A model that stays close to its priors but ignores the data is useless. The sweet spot, low free energy, is a model that updates just enough to explain what it sees, and no further. KL divergence does a lot of work in this framework, so here is the concrete version. KL divergence measures how different two probability distributions are. If Q equals P, if the beliefs perfectly match the prior, the divergence is 0. As Q drifts from P, the divergence grows. It is always non-negative and it is asymmetric. The distance from Q to P is not the same as the distance from P to Q. Think of it as, how surprised would I be if I sampled from Q but expected P? Here is a concrete example. Suppose your prior belief is that a coin is fair, 50% heads, 50% tails. You flip it 10 times and get 9 heads. Your updated belief might be 90% heads. The KL divergence between these two distributions, fair coin versus biased coin, is about 0.37 nats. Not huge, but not zero. The free energy framework says, accept this update only if the evidence is strong enough to justify the complexity cost. Here is a second example that shows how the acceptance criterion works. Your prior belief about an object is 70% chance it is falling, 30% chance it is hovering. New sensory evidence arrives, the object is not moving downward. Your posterior shifts, 20% falling, 80% hovering. The KL divergence for this update is about 0.84 nats, a meaningful shift from the prior. Should the system accept this update? It depends on the accuracy gain. If the new belief improves the predicted log likelihood of the observed data by 1.5 nats, the net free energy drops, the accuracy gain outweighs the complexity cost. Update accepted. But if the same belief shift only improved log likelihood by 0.2 nats, the complexity cost wins. The system should not fully commit to the new belief based on weak evidence. It should partially update, shift the distribution slightly toward hovering but maintain substantial weight on falling until more evidence arrives. This is principled conservatism. The system does not reject evidence. It weights it against the cost of changing its mind. Strong evidence produces large updates. Weak evidence produces small ones. The balance is automatic. In the free energy framework, KL divergence appears twice. Once as the complexity cost, beliefs versus prior. And once, implicitly, as the gap between the approximate beliefs and the true. Posterior, the distribution the system would hold if it could do exact inference. Minimizing free energy drives this gap down, making the approximate beliefs a better and better approximation of the truth. This is the mechanism by which a system learns. Not by adjusting weights via gradient descent. By adjusting probability distributions via free energy minimization. The updates are local, principled, and continuous. The system does not need a pre-collected label training set. It learns from every observation online, updating continuously as new data arrives. The IRI Swarm API performs the same computation implicitly. Each extraction worker produces observations with confidence scores. The supervisor examines the blackboard and compares the accumulated observations against the queries it needs to answer. Where the blackboard provides high confidence, well-supported answers, the supervisor considers those areas converged, low free energy. Where the answers are thin, contradictory, or missing, the supervisor identifies those as high free energy regions and dispatches targeted follow-up workers. The system allocates resources where uncertainty is highest, just as free energy minimization directs belief updates where prediction error is largest. We are about to turn all of this theory into a machine that plays Atari games better than systems with 400 times more parameters. We have the principle, minimize free energy. We have the math, beliefs are distributions, free energy balances accuracy and complexity, updates follow KL divergence. Now we need the engineering. Active Inference is the engineering framework that turns the free energy principle into a working agent. The move from principle to engineering requires one critical addition, a generative model. In standard machine learning, a discriminative model takes an input and produces a label. Show it a picture, it outputs cat. It learns the boundary between categories. It does not know anything about how cats produce images. If you ask it, what would a cat look like if it were upside down in a swimming pool, it cannot generate that. It only knows how to classify images it receives. A generative model works the other direction. It starts with hypotheses about the hidden causes of the data there. is a cat at position X, Y, with color C and pose P, and it generates the expected sensory data those causes would produce. If a tabby cat were sitting on the left side of the frame, this is what the pixel pattern should look like. This distinction matters because a generative model can do three things a discriminative model cannot. First, it can simulate. Given a set of causes, it can generate what the world should look like. A discriminative model trained to classify animals from photos can tell you this is a dog. A generative model can tell you if there were a brown dog standing on grass under cloudy sky, the image would look like this. The discriminative model goes from effects to labels. The generative model goes from causes to predicted effects. Second, it can predict consequences. If I move this piece, my opponent's queen will be threatened. The generative model rolls forward in time by applying the causal structure. A discriminative model would need to have seen that exact board position in its training data. Third, it can diagnose. When a prediction fails, it can trace back to which specific cause was wrong. The ball did not go where expected. Was the velocity wrong? The angle? The presence of a wall? Because the model has explicit causes, it can identify which one produced the error. A discriminative model just knows it was wrong, it cannot tell you why. The agent maintains beliefs about the hidden causes. It runs them through the generative model to produce predicted sensory data. It compares the predictions to the actual sensory input. The mismatch is the prediction error. The free energy. The agent then updates its beliefs about the hidden causes to reduce this error. This is perception, inferring causes from effects by inverting the generative model. Here is a concrete example. The agent sees pixels on the screen. Its generative model says, if there is a red ball at position 50, 30, the pixels in that region should be red and circular. The agent compares this prediction to the actual pixels. If the pixels match red and circular in that region, the prediction error is low, and the belief there is a red ball at 50, 30 is confirmed. If the pixels are blue, the prediction error is high, and the belief must be updated. Maybe the ball moved, maybe it changed color, maybe it was never a ball. This is the inverse problem. The agent does not classify pixels into categories. It hypothesizes causes and checks whether the predicted effects match reality. This is how science works. This is how diagnosis works. This is how debugging works. But active inference does not stop at perception. The agent also selects actions. The agent has preferences, states of the world it wants to inhabit. These preferences are encoded as prior beliefs about future observations. I prefer to be in a state where my health is full and my score is high. These are not reward functions bolted onto the system from outside. They are part of the generative model itself. They are beliefs about what observations the agent expects to encounter in the future. This is a load-bearing difference from reinforcement learning. In RL, the reward function is separate from the model. It sits outside the agent. A human designer defines what is rewarding, +1 for catching the ball, -1 for dying, 0 for everything else. The agent does not have beliefs about what it should observe, it receives reward signals after the fact and adjusts its policy to get more of them. The reward function is an external judgment, not an internal expectation. In active inference, the preferences are part of the model. The agent believes it should observe high scores, just as strongly as it believes that balls fall downward. When it observes a low score, that is prediction error, the same kind of error as a failed physics prediction. The agent acts to resolve it. Consider what this means concretely. An active inference agent playing a game has a generative model that says, in the future, I expect to observe a high score, full health, and no collision with enemies. When the agent observes a collision with an enemy and a health decrease, that is prediction error across two dimensions, the collision it did not expect, and the health decrease it did not expect. Both errors drive the agent to act to avoid future collisions and maintain health. The elegance is that the same mechanism handles physics and goals. Balls fall is a belief about the world. I should have high health is a belief about the future. Both generate predictions. Both produce prediction error when violated. Both drive the agent to reduce the gap. To select actions, the agent uses its generative model to simulate possible futures. If I move left, what will I observe? If I move right? If I jump? It rolls out the consequences of each action through its internal model and scores each trajectory by how well the predicted observations match its preferences. Then it picks the action that produces the best predicted future. And it executes only the first step. Then it observes the actual result, updates its beliefs, and plans again. This is called a predict-act-observe-update loop. It runs continuously. The model never stops learning. Every observation is an opportunity to revise a belief. Every action is an opportunity to test a hypothesis. The loop looks like this: believe, predict, act, observe, compare, update, believe again. Each cycle tightens the model. Each cycle reduces free energy. The agent becomes more accurate with every iteration. Notice something about this loop that separates it from every training paradigm in deep learning: there is no separation between training and deployment. The loop runs continuously. The agent is always learning. It does not have a training phase where it ingests data and a deployment phase where it applies what it learned. Every deployment moment is also a training moment. Every observation refines the model. The agent that plays the game at frame 10,000 is different from the agent at frame 100, not because someone retrained it, but because it has been updating its beliefs for 9,900 frames. Compare this to a deep RL agent. The RL agent has a policy network that maps states to actions. It was trained over millions of episodes. When deployed, it applies the policy. If the environment changes, the policy is wrong. The only fix is retraining. There is no model to update, no belief to revise, no prediction to test. The RL agent is a lookup table with smooth interpolation. The Active Inference agent is a scientist running continuous experiments. The IRI Swarm API runs the same loop at the document level. The blackboard is the model. Extraction workers generate predictions about document content typed observations. The supervisor compares the blackboard's coverage to the queries it needs to answer. Where coverage is thin, it dispatches targeted workers. Each iteration tightens the blackboard. The loop runs until the system's understanding converges. No pre-training. No fixed number of passes. The system decides when it is done, based on whether its predictions, its answers to queries, are still producing high error. Now that we understand the basic loop, we need to understand how the agent chooses which experiments to run. This brings us to planning. Most planning systems optimize for reward. Given a model of the world, simulate possible futures, and pick the action sequence that maximizes expected cumulative reward. This works when you know the model well. It breaks when the model is uncertain. Consider a concrete example. An agent is in a grid world, a maze with rooms, corridors, and rewards hidden in some rooms. The agent has explored the left half of the maze and found a small reward A. Score of 10 in one of the rooms. It has not explored the right half. A reward-only planner, the kind used in standard RL, would head directly toward the known reward. Score of 10 is better than the unknown. The agent exploits. But the right half of the maze might contain a score of 100. The agent would never find it, because it never looks. Worse, the agent does not even know what it does not know. It has no mechanism for valuing the information it would gain by exploring. This is the exploration-exploitation trade-off, and it has haunted reinforcement learning for decades. Exploiting known rewards gives immediate payoff. Exploring unknown territory gives information that might lead to better payoffs later. The optimal balance depends on the agent's current knowledge, the remaining time, and the structure of the environment. In practice, most RL systems handle exploration crudely. Epsilon Greedy says, with probability 0.1, take a random action instead of the best known action. This means 10% of the time, the agent moves randomly, which sometimes leads it to new rooms, and sometimes leads it into walls it has already explored. The exploration is uniform, unintelligent, and wasteful. Active Inference dissolves this trade-off entirely. Active Inference optimizes for expected free energy, which naturally decomposes into two components. The first is pragmatic value. Will this action lead to observations the agent prefers? This is the familiar reward-seeking component. If I move the paddle to the left, the ball will hit it and I will score a point. Pragmatic value pulls the agent toward known rewards. The second is epistemic value. Will this action reduce the agent's uncertainty about the world? This is the component that produces curiosity. If I move to the unexplored corner of the map, I will learn what is there. Even if there is no immediate reward, I will gain information that makes my model of the world more accurate. That information will make all of my future decisions better. Epistemic value pulls the agent toward the unknown. This is not a heuristic. It is not an exploration bonus bolted onto the reward function. It falls directly out of the mathematics of expected free energy. When you derive what action minimizes expected future free energy, you get a quantity that naturally balances reward seeking and information seeking. The math looks like this. The expected free energy for a future action sequence decomposes into a term that measures how well the predicted observations match preferences, pragmatic value, and a term that measures the expected information gain, how much the agent expects to learn from those observations, epistemic value. Both terms come from the same derivation. Neither is added by hand. In reinforcement learning, exploration is a problem you solve with tricks epsilon greedy, softmax temperature, intrinsic motivation modules, curiosity bonuses, count-based exploration. Each is a separate mechanism, a hack layered on top of the core objective. Epsilon greedy says, with probability epsilon, pick a random action. This is crude. It wastes exploration on actions that provide no information. It explores uniformly when it should explore strategically. Curiosity bonuses say, add a reward for novel states. This is better, but it requires a separate neural network to estimate novelty, which must itself be trained, which introduces its own failure modes. And the curiosity bonus must be calibrated against the real reward, too high and the agent ignores reward to chase novelty, too low and it never explores. In active inference, exploration is not a problem. It is a consequence. The same objective that drives the agent toward reward also drives it toward information. Let me put numbers on this. An agent stands at a junction. Two actions are available. Action A leads to a known reward region, expected reward score of 12, expected information gain of 0.4 nats. Action B leads to an unexplored corridor, expected reward score of 6, expected information gain of 2.7 nats. On a pure reward planner, action A wins every time. Score 12 beats score 6. The agent never explores the corridor. On expected free energy, the combined objective weighs both terms. Early in learning, when the model is uncertain, the information term dominates. Action B wins because 2.7 nats of uncertainty reduction is worth more than 6 points of additional reward. The information will improve every future decision. The agent explores. 2 replans later, the agent has explored the corridor and its information gain for that region drops to 0.4 nats. Now action A wins, the pragmatic value dominates because the model is already accurate. The agent exploits. The Transition from exploration to exploitation is smooth, automatic, and mathematically principled. No tuning required. The IRI Swarm API supervisor uses the same principle in a completely different domain. When the supervisor examines the blackboard after an extraction pass, it identifies the highest uncertainty regions, the gaps where the system's understanding is thinnest. It dispatches follow-up workers to those specific regions. This is epistemic action, allocating resources to reduce uncertainty where it matters most. Here is what this looks like concretely. After the first extraction pass on a merger agreement, the blackboard has strong entries for parties, dates, and basic terms. But the indemnity section produced a gap entry. The extraction was ambiguous about whether the cap applies per claim or aggregate. The supervisor does not reread the entire 200-page agreement. It dispatches a single follow-up worker to the indemnity section, with the specific instruction to resolve whether the cap is per claim or aggregate. That worker reads 5 pages, produces a definitive observation, and the gap closes. The system spent tokens on 5 pages, not 200. The result is focused investigation, not redundant rereading. The system does not reprocess documents it already understands well. It targets the gaps. As the blackboard converges, as the system's model of the document set becomes more complete, the supervisor allocates fewer follow-up workers. Eventually, the understanding is sufficient and the system stops. The transition from exploration, extracting new information, to exploitation, synthesizing complete answers, happens naturally as the blackboard fills. That is how an active inference agent plans. But how does it differ from reinforcement learning in structure, not just in philosophy? The differences are deeper than the planning objective. This is a good point to be explicit about the structural differences, because people often ask, is active inference just model-based RL with a different loss function? No. The differences go deeper than the loss function. They go to what the system represents, how it learns, and how it adapts. In reinforcement learning, the agent learns a policy, a function from states to actions that maximizes cumulative reward. The state representation is either hand-designed or learned end-to-end via a neural network. The agent tries actions, observes rewards, and adjusts the policy. The knowledge lives in the weights of the policy network. In active inference, the agent learns a generative model, a structured description of how the world works. The model has explicit components, states, transitions, observations, preferences. The knowledge lives in probability distributions over these components. The agent does not. Have a policy in the RL sense. It plans online, at every time step, by simulating futures through its model. Consequence 1: Sample efficiency. An RL agent needs thousands or millions of episodes to converge on a good policy, because it is learning associations between states and actions through trial and error. Each episode provides one data point. I tried this sequence of actions, and the total reward was this number. The gradient update is noisy and high variance. An active inference agent can learn from a handful of observations, because each observation directly updates its causal model. Seeing one ball bounce teaches it about bouncing. Seeing one object fall teaches it about gravity. The model transfers instantly to all objects that fall or bounce. In concrete numbers, AXIOM achieves human-level play in Atari-style games within 10,000 frames. Deep RL baselines require millions of frames for comparable performance. That is a 100 to 1000x data efficiency gap. Consequence 2: Adaptability. When the environment changes, a rule shifts, a color swaps, physics behave differently, the RL agent's policy is wrong. It was optimized for the old environment. Adapting requires retraining, which requires new data from the changed environment, which requires time and compute. During the retraining period, the agent performs badly. An active inference agent handles the same change differently. Its predictions fail. Prediction error spikes. The agent updates the specific component of its model that produced the wrong prediction. The update is local, it does not disturb unrelated beliefs. The agent adapts online. AXIOM's perturbation experiments show zero retraining recovery within tens of frames in these environments. Here is a concrete example. Imagine a simple game where a ball falls from the top of the screen and the agent controls a paddle at the bottom to catch it. A deep RL agent learns, when the ball is at position X, Y, move the paddle toward X. After millions of frames, the policy is smooth and accurate. The agent catches most balls. Now change the game. The ball still falls, but now it bounces off a wall halfway down the screen, changing direction. The RL agent's policy was trained on the old trajectory. It moves the paddle toward where the ball would have gone without the bounce. It misses. An active inference agent has a model: balls fall with gravity, balls bounce off surfaces, the angle of bounce depends on the angle of impact. When the wall appears, the first ball bounces. The agent's prediction, the ball should continue falling straight, fails. Prediction error spikes. The agent updates, there is a surface here, and balls bounce off it. From the very next ball, the agent predicts the new trajectory. It catches the ball. No retraining. No new data collection phase. One failed prediction, one model update, and the agent has adapted. This is the difference between a tourist who memorized a map and a local who understands the geography. When a road closes, the tourist is lost. The local reroutes immediately because they understand the structure, not just the routes. The difference also shows up in how the two systems handle ambiguity. Suppose the ball is partially occluded, hidden behind another object. The RL agent receives partial pixel input. Its policy was trained on full visibility frames. It either makes a random guess or freezes, because the input does not. Match any state it has seen. The active inference agent handles this differently. Its generative model predicts where the ball should be based on its last known position and velocity. Even though the pixels are occluded, the model maintains a belief about the ball's location, a wider Gaussian, reflecting higher uncertainty, but still a useful estimate. The agent acts on this estimate while simultaneously directing attention toward the region where the ball might reappear. It is uncertain, and it is using that uncertainty productively. This is what it looks like to have uncertainty as a first-class computational resource rather than a nuisance to be averaged away. Consequence 3, transparency. An RL agent's policy is a black box. You cannot inspect what it has learned or why it makes a specific decision. You can probe it with inputs and observe its outputs, but you cannot read its beliefs. An active inference agent's model is explicit. You can inspect its beliefs about each state variable. You can see its predictions. You can trace exactly which belief produced a wrong prediction and how it was updated. This is transparency by construction, not by post hoc explanation. This transparency property, the ability to inspect beliefs, trace predictions, and audit decisions, is the same property that makes the Iris Swarm API viable in regulated domains. An attorney cannot submit an AI-generated analysis to a court if they cannot explain where each conclusion came from. The Blackboard's typed provenance chain provides that explanation by construction, the same way AXIOM's explicit belief state provides it for gameplaying. These advantages are real. But they come with costs, and I want to be honest about them. Building a generative model is hard. Someone has to specify the structure, the variables, the transitions, the observation model. For AXIOM, this structure is the hierarchy of mixture models we are about to walk through. The field is still developing tools to make this easier. The no-code wrapper that Versa's built exists precisely because the raw framework is not yet accessible to non-experts. The ecosystem is embryonic. Deep learning has PyTorch, TensorFlow, JAX, Hugging Face, thousands of tutorials, and millions of practitioners. Active Inference has a handful of research groups and a few open-source implementations. The gap is closing, but it is wide. And scaling to complex continuous environments, real-world robotics, high-dimensional state spaces, long-time horizons, remains research-grade. AXIOM has proven the concept in Atari-style game environments. The path to general real-world deployment is promising, but Unfinished. Those are real limitations. But the benchmarks are also real. AXIOM beats deep RL baselines with approximately 400 times fewer parameters. Here is how it works. AXIOM stands for Active Expanding Inference with Object-Centric Models. It is built by Versus AI, and it is the first system to take active inference from theory to competitive benchmark results against state-of-the-art deep RL. Everything we have built so far, the free energy principle, active inference, expected free energy, the predict act observe update loop, converges here. AXIOM is where the theory becomes a machine. The architecture has 4 modules, stacked in a hierarchy. Each module handles a specific layer of cognition, and each passes its output to the next. We are going to take them apart one at a time. The first module is the slot mixture model, or SMM. It handles perception, the most basic question any intelligent system must answer: what am I looking at? Before an agent can reason, plan, or act, it must impose structure on raw sensory data. It must carve the world into discrete, persistent things that can be tracked, predicted, and controlled. Without objects, there is no reasoning. There are just pixels. AXIOM makes a bet about reality. A strong one: what you see on screen is generated by a small number of coherent, persistent objects moving and interacting over time. The visual world is not a soup of pixels. It is a composition of causes. Each object is a cause. The pixels are the effects. This is the generative model in action. The SMM does not classify pixels, it hypothesizes objects and generates predicted images from those hypotheses. To understand how, we need to build up the Gaussian mixture model from scratch, because the SMM is a specific application of the GMM idea. We already built the Gaussian in the last chapter, a bell curve with a mean and a variance. And we introduced the mixture, a sum of Gaussians, each with its own center, width, and weight. Now let us see how a mixture model actually learns. The algorithm is called expectation maximization, and it alternates between 2 steps. In the E step, the model holds its current parameters fixed and asks, given these parameters, which component probably generated each data point? It computes the responsibility, the probability that component K generated data point N. In the M step, the model holds the responsibilities fixed and asks, given these assignments, what are the best parameters for each component? It re-estimates the means. Variances, and mixing weights. E step, assign data to components. M step, update components to fit the data. Repeat until the assignments stop changing. Let me make this concrete with numbers. Suppose you have 6 data points on a number line, 1, 2, 3, 8, 9, 10. You suspect there are 2 clusters. You initialize 2 Gaussians, component A with mean 4 and component B with mean 7. E step. For data point 1, component A, mean 4, is closer. The responsibility of A for this point is high, say 0.95. Component B gets 0.05. For data point 9, component B, mean 7, is closer. B gets responsibility 0.9, A gets 0.1. You compute responsibilities for all 6 points. M step. Component A's new mean is the responsibility weighted average of all points. Points 1, 2, 3 contribute heavily. Points 8, 9, 10 contribute weakly. The new mean shifts toward 2. Component B's new mean shifts toward 9. Both variances tighten, each component is now more confident about its cluster. Repeat. After 3 iterations, component A has mean 2.0 and component B has mean 9.0. The responsibilities are nearly binary: A owns the left cluster, B owns the right. The algorithm has converged. No gradient descent. No loss landscape. No backpropagation. Just alternating assignment and parameter estimation. This is free energy minimization in disguise. The E step is perception, updating beliefs about which causes explain the data. The M step is model learning, updating the generative model to better predict the data. The alternation between the two is the same alternation between perception and action that the free energy principle describes. Now combine these tools and you have the SMM. Picture the process step by step, because this is where the abstract mathematics becomes a concrete perception engine. AXIOM receives a frame, a 210 by 160 pixel RGB image. It reshapes this into roughly 33,600 data points, each encoded as a 5-dimensional vector, red, green, blue color values, plus x and y spatial coordinates. Each slot in the SMM represents a hypothesis about an object. The slot contains a set of Gaussian beliefs. Where is the object? Position. What does it look like? Color. What shape does it have? These are not fixed labels. They are probability distributions, uncertain, updatable beliefs. Now the generative battle begins, and this is the core visual of the entire perception system. Each slot projects its beliefs into image space. If I exist, if a reddish spherical object is located in the top left region, this is what the pixels in my area should look like. Each slot generates a prediction. The SMM then compares all of these predictions against the actual image. For each pixel, it evaluates which slot's prediction was the best match. This is the E step. The pixels in the top left corner are well explained by the reddish slot's prediction, so that slot gets high responsibility for those pixels. Pixels in the bottom right might be better explained by a different slot, a blue rectangular object. That slot gets responsibility for those pixels. Then the M step, each slot updates its parameters, its mean color, mean position, and variance, based on the pixels assigned to it. The update is weighted by responsibility. A slot that explains 80% of the pixels in a region adjusts its parameters strongly toward the color and position of those pixels. A slot that explains only 10% adjusts weakly. After a few rounds of E step and M step, the slots have carved the scene into objects. The result is a soft, complete segmentation of the entire scene. Every pixel is assigned a probabilistic responsibility across all slots. Objects emerge from the competition between hypotheses. Let me make this concrete with numbers. Suppose the screen shows 3 objects, a red ball in the top left, a blue paddle at the bottom, and a green enemy in the center. The SMM starts with, say, 10 slots all initialized with vague, spread out beliefs about color and position. After the E step, most of the pixels in the top left region have high responsibility assigned to slot 3, the slot whose initial beliefs happen to be closest to the red, top left pixel pattern. The bottom pixels cluster around slot 7. The center pixels cluster around slot 1. The remaining 7 slots have near zero responsibility everywhere they are unused. After the M step, slot 3's mean color has moved toward red, R equals 200, G equals 30, B equals 30, its mean position has moved toward 40, 30, and its variance has tightened. Slot 7 has converged on blue in the bottom of the screen. Slot 1. Has converged on green and the center. 3 rounds of E step and M step, and the system has segmented the scene into 3 objects with no labels, no training data, and no gradient descent. The entire perception model for this frame is 3 sets of Gaussian parameters, about 30 numbers total. This produces 3 properties that deep learning cannot easily match. First, extreme efficiency. AXIOM is not learning pixel patterns through gradient descent over a training set. It is learning the parameters of a handful of Gaussian distributions from the current frame. The paper states this operates without the computational expense of gradient-based optimization. Each object is described by its mean and variance in 5 dimensions, that is 10 numbers per object. If there are 20 objects on screen, the entire perception model has 200 numbers. A convolutional neural network for the same task would need millions of weights. AXIOM learns a new game from 10,000 interaction steps because it is learning a compact model of the world's underlying structure, a few Gaussian parameters per object, not a bloated map of surface features. The model uses 400 times fewer parameters than comparable deep RL systems because the problem it is solving is simpler and more correct. Second, inherent plasticity. What happens when a new, unforeseen object appears? The SMM uses a truncated stick-breaking prior, a mechanism that lets the model decide when none of its existing slots can adequately explain a new piece of data. Here is how stick breaking works. Imagine you have a stick of unit length, it represents 100% of the data. You break off a piece. That first piece is the mixing weight for the first component. The remaining stick represents the data not yet explained. You break off another piece from the remainder. That is the weight for the second component. You keep going. The truncation means you start with a maximum number of slots, say, 30. Most of them have tiny weights, they explain almost nothing. When a new object appears that none of the existing high weight slots can explain, one of the small weight slots grows. The system promotes it from negligible to active. None of my existing objects can explain this new red thing. I hypothesize a new object and will now model it. The system grows its own complexity to match its environment. Third, no training data required. The SMM does not need labeled examples. It does not need someone to draw bounding boxes around objects in a training set. It does not need a pre-training phase on ImageNet. It learns from the raw pixels of the current frame. Every new game is a fresh start, and the system reaches competent perception within hundreds of frames, not millions. Drop the SMM into a game it has never seen different objects, different colors, different layout, and it segments the scene within the first. Few hundred frames. No transfer learning. No domain adaptation. The algorithm is the same. The data is new. The result is new objects, discovered from scratch. This is the same principle the Iris Swarm API uses at the document level. Specialized extraction workers are assigned to document subsets. Each worker generates structured observations from its assigned documents. The blackboard accumulates these observations without any domain-specific training. The same architecture processes legal briefs, 10K financial filings, compliance documents, and research papers. No domain-specific training. No pre-training. The extraction logic is general purpose, just like the SMM's pixel-to-object logic. When the Iris system encounters a document type it has not processed before, a new contract format, a different regulatory filing structure, it does not depend on a single hard-coded template. The swarm can create gap entries, dispatch follow-up extraction, and preserve uncertainty when the structure is unfamiliar. The architecture is built around general observation types, not brittle per-format logic. This is the document-level equivalent of the SMM's stick-breaking prior, grow new understanding when existing structures are insufficient. The SMM gives us the nouns of the scene, the objects. But perception alone is not intelligence. The agent needs to know what kinds of things these objects are and how they behave over time. That requires the next two modules. The SMM carves the world into objects. But a world of objects is a snapshot, it is static. To be intelligent, the agent needs verbs. It needs to understand what happens over time. It needs process. Consider a red circle on screen. Is it a harmless fruit that gives points when collected? Or a falling bomb that kills the player on contact? The visual appearance is identical, same color, same shape, same size. The SMM knows where it is and what color it is. But it does not know what type of thing it is, or how it will behave. That requires two more modules. The first is the Identity Mixture Model, or IMM. It answers the question, what kind of thing is this? The problem it solves is load-bearing. Suppose the agent has learned that red spheres bounce and green cubes explode. A new red sphere appears. If the system treats this as a completely new object, requiring fresh motion learning and reward mapping from scratch, it has wasted everything it already knew about red spheres. Worse, what happens when the red sphere turns blue mid-game because of a visual glitch or lighting change? If the system ties identity to color, it loses the object entirely. All the learned dynamics for that object, how it moves, what it does when you interact with it, whether it is dangerous, are now inaccessible because the color changed. This is the problem of invariant identity. Humans solve it effortlessly. You recognize your friend even when they change their hair color. You recognize a car as a car whether it is red, blue, or silver. Your identity system is independent of surface features. It runs on deeper structure. The IMM solves this by assigning identity codes. Not instance-level labels like red ball number 1. Type-level labels like ball. It analyzes the continuous features of each slot, color distribution, shape parameters, typical position ranges, and clusters objects into types. Objects with similar structural properties share an identity code, even if their surface features differ. This enables three things. First, the agent reuses learned dynamics across instances. If it knows how ball objects move, every new ball benefits immediately. No relearning. No data hunger. One example teaches the type. Second, it recovers from perturbations. When a color change occurs mid-game, the IMM initially creates new identity slots for the unfamiliar colors. But then something interesting happens. The system notices that the new slots have the same shape, the same size, the same motion patterns as the old ones. The only difference is color. Using persistent shape features, the IMM remaps the objects to their original identity codes. The agent recovers its old knowledge about that object type instantly. No retraining. Third, it reasons abstractly. The agent can think about type of thing rather than exact thing, which is how. Generalization works. All bombs explode when you touch them is more useful than this specific red circle at position 40, 80, explodes when you touch it. The perturbation experiments in the paper prove this. When object colors are changed mid-game, the IMM initially creates new identity slots for the unfamiliar colors. But once color remapping activates, based on persistent shape, the objects are correctly reassigned to their original identity codes. The agent resumes its learned behavior without retraining. The iris blackboard carries the same structure. Every entry is typed observation, calculation, gap, analysis, with source provenance and identity tracked. The typing is not just metadata. It is the mechanism that enables generalization. When the system processes a new contract in a matter and encounters a material adverse effect clause, it does not relearn what MAE clauses look like. The typed structure of the blackboard means it recognizes the observation type from previous contracts and applies the same extraction logic. A MAE clause in a merger agreement has the same type as a MAE clause in a stock purchase agreement, even though the specific language differs. The system generalizes at the type level, this is a MAE clause and I know what information to extract from MAE clauses, not at the instance level. Same principle as the IMM, type-level generalization over instance-level memorization. The second module at this level is the Transition Mixture Model, or TMM. It answers the question, how do things move? The TMM is AXIOM's physics engine. But unlike a hand-coded physics engine, the TMM builds itself from observation. It learns a shared library of linear dynamics modes. Think of each mode as a simple rule governing how an object's state changes from one frame to the next. Mode 1, falling, the y-coordinate increases at a constant rate. This is a linear transformation, next underscore y equals current underscore y plus constant. Mode 2, bouncing, the y-coordinate reverses direction. The velocity flips sign. Mode 3, stationary, nothing changes. Next state equals current state. Mode 4, drifting right, the x-coordinate increases at a constant rate. Each mode is a matrix, a linear transformation that maps state at time t to state at time t plus 1. The state vector includes position, velocity, and any other relevant features. The matrix encodes the dynamics rule. Technically, this is a switching linear dynamical system. The system has multiple linear dynamics models and switches between them depending on context. At any given moment, one mode is active for each object. Here is a worked example. A ball is falling. Its state is, position equals 50, velocity equals 3. The TMM applies the falling mode matrix, next position equals 50 plus 3 is equal to 53. Next velocity equals 3 plus 1 is equal to 4, gravity adds to velocity. The prediction, the ball will be at position 53 with velocity 4 in the next frame. The ball hits the floor. The actual next state is position. The floor, velocity minus 3, reversed. The prediction error is high. The TMM switches to the bouncing mode. The bouncing mode matrix says, next velocity equals negative of current velocity. The switch was driven by prediction error, the falling mode made a bad prediction, so the system tries a different mode. The key, the system does not know the modes in advance. It learns them from observation. Picture the process, early in a game, every object's motion is surprising. The TMM starts with a single vague dynamics mode, things might move somehow. The first ball falls, and the falling pattern produces persistent prediction error against this vague mode. The system spawns a new mode, falling. The first ball bounces, and the bouncing pattern produces error against the falling mode. Another new mode, bouncing. A static wall produces zero motion, the system confirms the stationary mode. After a few hundred frames, the TMM has built a library of dynamics modes from scratch. The library is shared across all objects. The TMM does not learn separate falling rules for each object. It learns one falling rule and applies it to everything that falls. When a new object appears, one the system has never seen, it does not. Start from zero. It assigns the object to the most likely existing mode based on its first few frames of motion. If none of the existing modes fit, it spawns a new one. This is reused at the physics level, and it is why the model stays small. The compression is dramatic. Instead of learning a separate motion model for each of 20 objects, which would require 20 sets of dynamics parameters, the system learns 4 or 5 shared modes and assigns each object to a mode at each time step. The total parameter count stays low no matter how many objects appear. The logic engine sits at the top of the hierarchy. But to understand it, we first need the operating system these modules run on, Markov decision processes. A Markov process is a system where the future depends only on the present, not on the history. The mathematical statement is simple: the probability of the next state, given the entire history, equals the probability of the next state given only the current state. History is irrelevant once you know the present. The name comes from the Russian mathematician Andrei Markov, who formalized this property in the early 1900s while studying sequences of letters in Russian poetry. This sounds restrictive, but it is not as restrictive as it seems. The trick is to make the state rich enough to contain everything the system needs. Two game states with identical scores, health bars, positions, and inventories, even if they arose from completely different sequences of play, will lead to the same distribution of future states. The path you took does not matter. Only where you are now. Matters. This is the Markovian property: the state contains all the information needed to predict the future. A Markov decision process extends this by adding 3 elements. Actions: the agent can make choices that influence state transitions. In an Atari game, the actions might be move left, move right, jump, fire. Each action changes the state differently. Transitions: the probability of reaching each next state, given the current state and the chosen action. If the agent is at position 30, 50, and takes the move right action, the transition function says, with probability 0.9, the next state is position 32, 50. With probability 0.1, something else happens, maybe the agent collides with an obstacle and stays put. Rewards: each state action pair yields a signal about how good the outcome was. Catching a fruit gives +10. Colliding with an enemy gives -50. Standing still gives 0. The rewards define what the agent should care about. The MDP framework does not specify how the agent should behave. It specifies the rules of the game, the stage on which the agent performs. How the agent plays, its policy, its decision rule, is a separate question. In reinforcement learning, the agent learns a policy through trial and error. In active inference, the agent plans online using its generative model. AXIOM runs on this operating system. Every module, SMM, IM, TMM, and the RMM we are about to meet operates on the current state and transitions to the next. The Markovian structure is what makes the system tractable. The agent does not need to remember its entire history. It needs to maintain an accurate model of the present. Now we have perception, identity, and physics. One module remains, the one that ties everything together. We have perception, SMM, identity, IMM, and physics, TMM. The final module ties them all together, the recurrent mixture model, or RMM. This is the executive brain. The prefrontal cortex of the machine. The TMM gives the agent a library of motion rules. But a library is useless if you do not know which book to pull off the shelf. The RMM decides which rule applies right now. A ball in midair, the falling mode applies. The instant it hits the floor, the bouncing mode activates. But what triggers the switch? Context. The RMM takes the full context of the current moment and uses it to infer the correct dynamics mode. Its inputs are the object's own current state, position, velocity, size. Color, the identity and distance of the nearest interacting object, the action the agent just took, and the reward it just received. From these inputs, the RMM constructs a conditional distribution over dynamics modes. Given that my action was jump, the nearest object is an enemy of type spiky at a distance less than 5 pixels, and the last reward was negative, the most probable transition is governed by the dying dynamic. This is not a lookup table. It is a generative mixture model that infers the distribution over modes given the full context. Because the model is generative, it can handle novel combinations of familiar elements. It has never seen exactly this configuration before, this enemy type, at this distance, after this action, but it has seen each component, and the mixture model can compose them. Let me walk through a concrete example with the Mastermind code-breaking challenge, because this is where the RMM's causal reasoning produces its most dramatic results. Mastermind is a game where one player sets a secret code, a sequence of colored pegs, and the other player tries to guess it. After each guess, the code setter provides feedback: how many pegs are the right color in the right position, and how many are the right color in the wrong position. Here is how a human solves this. Suppose the secret code is 4 pegs, each one of 6 colors. There are 6 to the power of 4 possible codes, 1296. Guess 1, red, 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 red. Feedback: 0 correct position, 1 correct color. The human learns, one of the 4 positions should be red, but not in any of the positions tried. Hundreds of possible codes are eliminated. Guess 2, green, green, blue, blue. Feedback: 1 correct position, 1 correct color. The human combines this with the first guess. The constraints compound. Now fewer than 200 codes remain. Each guess is not just an attempt to be right. It is an experiment designed to maximize the information gained. The best next guess is the one that eliminates the most remaining possibilities regardless of what the feedback turns out to be. This is systematic constraint propagation. Each observation narrows the hypothesis space. After 4 or 5 guesses, the remaining possibilities narrow to 1. The code is solved. Versus Genius uses the same kind of structured stateful inference. It builds an explicit model of the game's rules, the relationship between guesses, feedback signals, and remaining possible codes. Each guess is an action. Each feedback signal is an observation. The RMM updates its beliefs about the hidden code based on the causal relationship between guesses and feedback. It performs systematic elimination, not pattern matching. Compare this to what an LLM does with Mastermind. The LLM generates a guess. It reads the feedback. It generates another guess. But it has no persistent model of which colors have been eliminated. It does. Not perform systematic constraint propagation. Each guess is informed only by what fits in the current context window. The LLM might forget that it already tried red in position 2 and got negative feedback. This is why DeepSeek R1 manages only a 45% success rate. It is pattern matching its way through a task that requires structured logical inference. The gap, 100% versus 45%, is not a performance tuning issue. It is a structural limitation. No amount of prompt engineering or chain of thought will give an LLM the persistent, structured belief state that Mastermind requires. The RMM has that state by construction. The RMM's power comes from compositionality. It has never seen exactly this configuration before, this enemy type, at this distance, after this action, with this reward signal, but it has seen each element separately. The mixture model composes them. It does not need an example of every possible combination. It needs examples of the components, and the generative structure handles the combinations. This is the same principle that lets you understand a sentence you have never heard before. You know the meanings of the words. You know the grammar. You compose them. You do not need a training example for every possible sentence. The RMM works the same way. It knows what enemy nearby means, what jump means, what negative reward means. It composes them into a new situation and infers the right dynamics mode. The RMM also enables something an LLM cannot: transparent failure diagnosis. When the RMM makes a wrong prediction, you can inspect exactly which context led to which mode selection. You can see the object states, the distances, the action taken. You can trace the causal chain from input to prediction to error. This is debugging by reading the model's beliefs, not by guessing at what a black box might have learned. The IRE synthesis workers operate the same way. When two observations in the blackboard contradict each other, document A says the threshold is 49% and document B says the threshold is 50%, the synthesis worker does not guess which one is correct. It traces the provenance chain. It identifies the source documents, the extraction workers, the iteration numbers. It produces an analysis entry that says exactly where the discrepancy came from and what it means. When the system fails, you know why. When it succeeds, you can prove it. This is auditability by construction. And in regulated domains, legal, finance, healthcare, it is not optional. An attorney is professionally responsible for the accuracy of their work product. A system that produces correct answers 83% of the time is useful only if the remaining 17% can be identified and corrected. The blackboard's provenance structure is the mechanism that makes this possible. We have walked through the 4 modules: perception, identity, physics, and logic. But we have described them as if their structure is fixed. It is not. The most striking property of AXIOM is that it structures itself. 3 processes govern this self-organization, and understanding them is the key to understanding why the system is so data efficient. The first process is expansion. When the prediction error from existing components is persistently too high, when the system is consistently surprised, it spawns new components. A new visual pattern that none of the existing slots can explain? The SMM grows a new slot. A new combination of color and shape that does not match any known identity code? the IMM adds a new identity. A trajectory of movement that none of the existing dynamics modes can predict? The TMM spawns a new mode. An interaction pattern with unfamiliar outcomes? The RMM adds a new causal cluster. The trigger is not novelty. It is persistent prediction error. A momentary spike in surprise is handled by updating beliefs. The ball bounced at an odd angle, update the trajectory prediction. But when the error stays high, when the existing model is systematically wrong over multiple frames, that is the signal to grow. This is a distinction with real consequences. A system that grows on every novel observation would explode in complexity. A system that grows only on persistent failure adds exactly the structure needed. AXIOM stick breaking prior controls this. New components start with near zero weight and only grow if they consistently reduce prediction error. This is why AXIOM adapts in 10,000 frames where deep RL agents still struggle after millions. It does not wait for gradient descent to slowly shift weights across the entire network. It adds exactly the new. Structure needed to explain what the old structure could not. The learning is targeted, not diffuse. The second process is pruning. Growth without governance is entropy. AXIOM periodically runs Bayesian model reduction every few hundred frames, just enough time to accumulate experience. It selects pairs of similar components and tests. What happens if we merge them? Let me walk through a concrete example. Early in a game, the agent encounters a red ball that bounces off the floor. The TMM creates a dynamics mode for this behavior, red ball bouncing. A few frames later, a blue square bounces off the floor. The TMM creates another mode, blue square bouncing. Bayesian model reduction asks, are these two modes really different? Or is the underlying dynamic the same? Things bounce off floors, with only surface features differing? The test is quantitative. The system computes the model evidence, the free energy, for two hypotheses. Hypothesis A, two separate modes, each specialized. Mode 1 has free energy 1.8. Mode 2 has free energy 1.9. Total cost of maintaining both, 3.7 plus the overhead of carrying two separate parameter sets. Hypothesis B, one merged mode, general. Free energy of the merged mode, 1.6. The merged model predicts the data better. And costs less to maintain. Merge accepted. But suppose the merged mode had free energy 2.5 worse than either individual mode. That means the merge loses prediction quality. The system keeps both modes separate. The red ball bouncing and the blue square bouncing really do behave differently. Maybe the square has friction and the ball does not. The system preserves that distinction. This is the control point. Complexity is cut only when prediction quality is not hurt. The system has generalized. It now knows, objects bounce off floors, regardless of color and shape. Concretely, getting hurt when a red ball hits the floor and getting hurt when a blue square hits the floor, are these two different phenomena, or one? The system merges them into things hitting the floor cause damage and checks whether the merged model predicts outcomes as well as the unmerged version. If yes, the merge is accepted. If not, the components remain separate. This produces generalization from small numbers of events. A single experience, one red ball hitting the floor, one blue square hitting the floor, can be compressed into a general rule. The system does not need hundreds of examples to generalize. One example per case is enough, because the pruning process tests the generalization explicitly rather than hoping gradient descent will find it. The ablation studies confirm this. Removing Bayesian model reduction from AXIOM hurts generalization performance. The system grows new components but never consolidates them, which leaves it with redundant, overly specific rules that fail to transfer. The third process is planning. We touched on this earlier, but now we can see how it sits in the full architecture. AXIOM uses model predictive control. At every frame, it samples multiple hypothetical action sequences. For each, it rolls out the consequences through its current world model using the TMM for dynamics prediction and the RMM for mode selection. It scores each trajectory on expected free energy. How much reward does this future contain, and how much will I learn from it? It refines the distribution of action sequences using the cross-entropy method. Here is how CEM works. You start with a distribution over action sequences, initially uniform. You sample a batch of sequences from this distribution. You evaluate each one by rolling it through the world model. You keep the top performing sequences, say, the top 10%. You refit the distribution to these elite sequences. The new distribution is tighter, centered on good action sequences. You sample again from this refined distribution, evaluate, and keep the best. After a few rounds, the distribution has converged on high-quality action sequences. Here is a concrete planning example. The agent is playing a game with a falling ball, a paddle, and an enemy. The agent considers 64 possible action sequences, each 10 steps long. For each sequence, it rolls out the world model. Sequence 1, move left 4. Ten steps. The ball falls to the right. The paddle misses. Expected reward, low. Information gain, 0, the agent already knows what is on the left. Sequence 17, move right for 5 steps, then jump. The paddle catches the ball. Score +10. But the jump puts the agent near the enemy. Expected reward, moderate. Information gain, low. Sequence 42, move right for 3 steps, stay for 2, move left for 5. The paddle catches the ball, avoids the enemy, and ends in an unexplored region. Expected reward, good. Information gain, high, the agent will learn about the unexplored region. Sequence 42 wins on expected free energy, it balances reward and information. The agent executes the first action, move right. Then it observes what happens, updates its beliefs, and plans again from the new state. The agent executes only the first action of the best sequence. Then it observes the result, updates its beliefs, and replans. This is model predictive control. Plan a full trajectory, execute one step, replan. It is the same control strategy used in robotics, process control, and autonomous driving. The planning is fast because the model is Markovian and factorized. There are no replay buffers, no value function networks, no backwards passes through deep networks. The computation scales linearly with the number of components and the planning horizon. The IRE swarm uses the same 3-part structure. Expansion: when the supervisor identifies gaps in the blackboard, it dispatches targeted follow-up workers to fill them. The system grows its understanding where it is insufficient. Compression: when the understanding is complete, the system stops. It does not continue rereading documents it already understands. The blackboard is the persistent state that makes both possible. It tracks what has been learned and what remains uncertain. Planning: the supervisor examines the blackboard and decides which extraction or synthesis tasks to dispatch next, targeting the highest uncertainty regions first. Picture the 3 processes running simultaneously. The system encounters something new, it grows a component to explain it. It notices 2 components are doing the same job, it merges them. It identifies an area of high uncertainty, it plans an action to investigate. Growth, compression, and exploration happening in parallel, frame after frame. The 3 processes form a complete cognitive loop. The system grows when the world is more complex than its current model. It shrinks when the model has redundancies. It acts to resolve remaining uncertainty. This loop is what makes AXIOM self-structuring. It does not need a human to decide how many slots or modes to use. It figures that out itself. Compare this to how a deep learning system handles the same lifecycle. Growth: you increase the network size by adding more layers or wider layers. This requires retraining from scratch. Compression: you apply pruning or distillation after training. This is a separate process, not part of the learning loop. Exploration: you add epsilon greedy randomness or curiosity bonuses. These are bolted on. In AXIOM, all 3 are consequences of the same free energy objective. In deep learning, they are separate engineering decisions made by separate teams using separate tools. The analogy to biological intelligence is deliberate. Your brain does not have a training phase. It is always learning. Every conversation, every new face, every stumble on an uneven sidewalk updates the model. The distinction between learning and doing. Is an artifact of how we build deep learning systems, not a property of intelligence itself. Now that we understand the full architecture, the question is, does it actually work? Time to look at the numbers. Theory and architecture are necessary but not sufficient. The question that matters is, does it work? And the answer requires context about how the evaluation was done, not just the headline numbers. AXIOM was tested on the Game World 10K benchmark, a suite of 10 Atari-style game environments specifically designed to test the capabilities that Active Inference claims to provide. These are not the classic Atari 2600 games from the arcade learning environment, they are purpose-built environments that isolate different aspects of intelligence: spatial reasoning, reward seeking, obstacle avoidance, timing, and multi-object interaction. Each environment has specific properties. Some have moving hazards that require timing. Some have multiple object types that require identity discrimination. Some have sparse rewards that require exploration. Some have combinatorial object interactions that require causal reasoning. The suite is designed so that different capabilities matter in different games. The benchmark name, 10K, refers to the data budget. Each system gets exactly 10,000 interaction frames to learn. This is the evaluation's core constraint. It forces the question, given severely limited experience, how quickly can a system learn to play? Why 10,000 frames? At 30 frames per second, that is about 5.5 minutes of gameplay. This is roughly how long it takes a human to figure out a simple game: a few minutes of poking around, dying a few times, understanding the basic rules, and starting to play competently. The benchmark asks, can a system learn as fast as a human does? Most deep RL systems cannot. They need millions of frames, hours, or days of gameplay to reach comparable performance. The 10K constraint exposes this gap directly. It is not a benchmark where you can compensate with more compute. You either learn efficiently or you do not. Human-level play, in this context, means the system achieves scores comparable to a human player who has had a similar amount of practice time, approximately 7 minutes. It does not mean superhuman. It does not mean the system has solved the game optimally. It means competent play under a tight data budget. AXIOM achieves this within 10,000 frames. 7 minutes of real-time interaction. The system goes from knowing nothing about the game, no rules, no physics, no object meanings, to competent play. It does this with 0.3 to 1.6 million parameters, depending on the environment. The variation comes from the self-structuring. More complex environments produce more slots, more modes, and more causal clusters, which means more parameters. But even at the top end, 1.6 million parameters is minuscule by modern standards. For comparison, deep RL baselines that achieve comparable performance on these environments use models with hundreds of millions of parameters and require millions of training frames. The parameter efficiency gap is approximately 400 to 1. The data efficiency gap is even larger, often 100 to 1000 to 1. The reason is structural. AXIOM does not need to learn pixel-level correlations across millions of frames. It learns a compact causal model, a handful of Gaussian parameters per object, a library of dynamics modes, a set of causal clusters. This model compresses the world into its essential structure, which is why it fits in so few parameters and learns from so little data. On the Mastermind Code-Breaking Challenge, the results are even more dramatic. Versus Genius achieves 100% success rate on this specific challenge. OpenAI's O1 preview achieves a lower success rate while using 140 times more time and 5,260 times more cost per solution. Against DeepSeek R1, which achieves a 45% success rate on the same challenge, Genius is 300 times faster and 800 times cheaper. These numbers come from a specific challenge that demands systematic logical inference, constraint propagation, process of elimination, and deterministic reasoning. The gap between LLM-based systems and causal inference on this task illustrates a structural limitation of pattern matching. It struggles with sequential logical reasoning where each step depends causally on the previous one. A persistent causal model handles this naturally. The perturbation experiments add another dimension, and they are the most revealing test in the paper. Mid-game, the experimenters change the colors of objects, or alter their shapes. They do this deliberately to test robustness, to see whether the system's competence depends on surface features or on deeper understanding. This is the test that separates memorization from modeling. A system that memorized avoid red things will behave incorrectly when red things turn green. A system that modeled avoid things of type hazard will track the identity through the color change. Deep RL baselines, trained on the original visual appearance, collapse. Their policies were tied to specific pixel patterns, and those patterns just changed. A policy that learned avoid the red thing has no mechanism for deciding what to do. When the red thing turns green, it either avoids the green thing, wrong, if green was previously safe, or ignores it, wrong, if the green thing is still dangerous. AXIOM adapts. Its IMM initially creates new identity slots for the unfamiliar appearances. Then, using persistent shape features, it remaps the objects back to their original identities. The agent resumes its learned behavior without retraining. The recovery is fast, within tens of frames, automatic, and driven by the same belief updating mechanism that handles normal perception. The ablation studies reveal which components matter. Remove Bayesian model reduction, and generalization suffers. The system grows complexity but never consolidates it, leaving it with redundant rules that fail to transfer. Remove information gained from the planning objective, and exploration suffers. The system only seeks reward and fails to investigate novel parts of the environment. It gets stuck in local optima because it never explores the state space strategically. The IRI Swarm API faces the same robustness challenge at the document level. When the system encounters a document format it has never processed before, a new regulatory filing structure, a different jurisdiction's contract template, the extraction workers do not crash. They produce observations with lower confidence scores and more gap entries. The supervisor identifies the high uncertainty regions and dispatches targeted follow-up. The system adapts to the unfamiliar format through the same iterative convergence that handles familiar formats, just with more iterations. Robustness to novel input is not a special feature. It is a property of the architecture. Both components are load-bearing. The architecture is not a collection of independent tricks. It is a coherent system where each part supports the others. Remove one piece and the others degrade, not because they crash, but because they lose the input they need to do their job well. The SMM needs the IMM for type generalization. The IMM needs the TMM for motion-based identity. The TMM needs the RMM for context-dependent mode selection. The RMM needs the SMM for object-level features. The modules are coupled through the generative model, and the coupling is what produces the emergent behavior. There is a strategic implication that goes beyond benchmarks. In the paper's experiments, AXIOM runs in real time on a single A100 GPU. For deployment, the target is edge hardware, NVIDIA Jetson-class devices that fit in a shoebox. Its planning time scales linearly with the number of simulated policies. Its inference time scales linearly with the number of SMM components. The system does not need GPU data centers. It does not need replay buffers. It does not need petabyte datasets. This changes who gets to build intelligent systems. The deep learning paradigm concentrates power. Training a frontier model is an enormous capital investment requiring large GPU clusters and access to proprietary data at web scale. Only a handful of organizations on the planet can afford it. The resulting models are opaque, brittle, and expensive to serve. Active inference, at least as implemented in AXIOM, inverts this. The models are small. The training is fast. The inference is cheap. The system is transparent. A research group with modest resources can build, test, and deploy an active inference agent. The gap is not just about cost. It is about capability distribution. When only 5 companies can build frontier AI, those 5 companies control what AI can do, who it serves, and how it is governed. When a university lab or a startup can build a system that outperforms the frontier on specific tasks, the power structure shifts. The question stops being can you afford the biggest model, and starts being can you build the smartest architecture? Versus describes pilot programs in Abu Dhabi's Smart City Initiative, targeting use cases like traffic coordination, disaster rescue, and network communications on edge hardware such as the NVIDIA Jetson AGX Thor. The deployment track record is still thin, this is early technology. But the target profile is clear: local, autonomous, real-time systems that work even when the network is down. Consider what this means for disaster response. When an earthquake hits and the cell towers fall, a cloud-based AI system stops working. An edge-deployed active inference system keeps running. It does not need a data center. It does not need an internet connection. It needs a small GPU and a power source. The intelligence is local. This is the democracy of intelligence, capable AI that does not require the largest compute budget. The implication is that the next generation of breakthrough AI systems might not come from the organization with the most GPUs. It might come from the team with the best architecture. The playing field is leveled when the bottleneck shifts from scale to structure. And this connects directly to what the Iris Swarm API is doing for knowledge work. The Iris Swarm API routes high-volume extraction to Gemini Flashlight at 25 cents per million input tokens. It reserves reasoning-heavy steps for Gemini Flash at $1.50 per million input tokens. On the 1251-task Harvey Legal Agent benchmark, this architecture achieved a 17.75% strict all-pass rate at $1.30 per task. Harvey's published baseline reports 10.4% strict all-pass at $50.90 per task. The same commodity models, coordinated through the Blackboard architecture, produced these results through structural coordination. Let me put those numbers in context. A 39x cost reduction is not a marginal improvement. It is a category shift. At $50.90 per task, processing a 1,000 document due diligence project costs roughly $50,000 in API calls alone. At $1.30 per task, the same project costs $1,300. That is the difference between only large law firms can afford AI and solo practitioners can afford AI. The technology is the same. The architecture is different. But the cost story goes deeper than per task pricing. The Iris Swarm API's Blackboard is persistent. Once the system has processed a document set and accumulated the observations on the Blackboard, subsequent queries against that same document set are cheap. The expensive part, reading the documents, extracting observations, resolving contradictions, happens once. Every subsequent question is answered by querying the Blackboard, not by rereading the documents. This is the read once, query forever economics. The first query against a 500 document set costs whatever the extraction costs. The second query costs a fraction of that, it reads the Blackboard, not the documents. The 100th query is nearly free. Here is what this looks like in practice. A due diligence set arrives as 1,000 source documents, contracts, amendments, side letters, correspondence. The first pass extraction writes typed entries to the Blackboard: parties, dates, indemnity thresholds, material adverse effect definitions, termination conditions, change of control provisions. That extraction pass is the expensive read. Every subsequent review. Question: which contracts have indemnity caps below 10 million? Or, are there any change of control provisions that trigger on a 30% ownership change? Reads the Blackboard, not the documents. The system dispatches follow-up workers only for items where the Blackboard is ambiguous or incomplete. It does not reread the entire corpus for every question. Compare this to a standard LLM approach where every query requires reprocessing the documents through the context window. Every question costs the same as the first question. There is no accumulation. There is no memory. Each interaction starts from scratch. The blackboard is the equivalent of AXIOM's world model, both persist structured state so the system does not repeat work it has already done. Both reject the stateless reinference paradigm that makes current AI systems expensive and brittle. The pattern is the same across both systems. AXIOM uses commodity-grade models, small, interpretable, and cheap, and achieves breakthrough results through architectural coordination. The Iris Swarm API uses commodity-grade LLMs and achieves breakthrough results through blackboard coordination. In AXIOM, structure reduces parameter count 400x. In Iris, structure reduces per task cost 39x. The models are cheap. The coordination is what produces the results. This matters because it means powerful AI is not gated by access to the most expensive hardware or the largest models. It is gated by architectural insight. And architectural insight is available to anyone who understands the principles. If this level of depth is valuable to you, the kind of explanation that connects physics to engineering to working systems and back, subscribe and like. Every video in this series aims to leave you with a complete understanding you can apply, not just facts you can repeat. The open source repository for the Iris Swarm API is available under MIT license. The architecture is documented. The benchmarks are reproducible. The system is available at iris.ai/iris-API for anyone who needs to reason over long documents cheaply and reliably. We have spent 2.5 hours building from physics to engineering to architecture to benchmarks. Step back now and look at the shape. Two systems from completely different domains arrived at the same structural insight independently. AXIOM, in the domain of game-playing AI, decompose cognition into modular specialized components. Give each component a bounded task. Let them share state through a common substrate. Let the system grow when surprised and compress when redundant. Use causal models instead of memorized associations. Plan by simulating futures through the model. Result: 400 times fewer parameters. $10,000 training frames instead of millions. Human-level play. Full transparency. Edge deployment. Iris stateful swarms, in the domain of document analysis, decompose analysis into specialized agent workers. Give each worker a bounded task. Let them share state through a persistent blackboard. Let the system converge iteratively, expand when gaps remain, stop when understanding is complete. Use structured provenance instead of opaque token sequences. Route work based on uncertainty. Result: 39 times lower cost. 17.75% strict all-pass versus 10.4%. Full auditability. Commodity model routing. Domain general architecture. The convergence is not a coincidence. It is not two teams copying each other. AXIOM comes from active inference research in neuroscience, and the Iris Swarm API comes from the practical problem of making legal AI affordable and reliable. The teams work in different fields, with different tools, on different problems. Yet they arrived at the same structural pattern. The same pattern keeps appearing because the problems have the same shape. Whether you are reasoning about Atari pixels or 1,000-page legal filings, the bottleneck is not the model size. It is the coordination of information processing. Decompose. Specialize. Share state. Iterate. Grow where uncertain. Compress where redundant. Audit by construction. The deep learning paradigm says, scale the model and the behavior will follow. The structural coordination thesis says, structure the coordination and the behavior will emerge from smaller, cheaper, more transparent components. Both AXIOM and the Iris Swarm API prove the second thesis. Frozen models that achieve nothing individually produce real results when coordinated through principled architecture. Let me make the mapping explicit, because the correspondence is specific. AXIOM's SMM segments pixels into objects. The Iris extraction workers segment documents into typed observations. Both convert raw input into structured, labeled units that downstream modules can reason about. The mechanism is the same: compete to explain data, assign responsibility, update parameters. AXIOM's IMM assigns type-level identity codes so the agent can generalize across instances. The Iris Blackboard schema assigns observation types extraction, calculation, gap, analysis so the system can generalize across document formats. Both separate what kind of thing is this from what does this specific instance look like. AXIOM's TMM learns shared dynamics modes, falling, bouncing, drifting, that apply across all objects. The Iris supervisor learns recurring extraction patterns, clause identification, threshold extraction, party enumeration, that apply across all document types. Both build a shared library of process knowledge that transfers to new instances. AXIOM's RMM infers which dynamics mode applies given the current context. The Iris supervisor infers which follow-up action to take given the current Blackboard state. Both select actions based on causal context, not on memorized associations. And underneath all four parallels, the same free energy logic, both systems allocate compute where uncertainty is highest. AXIOM's expected free energy sends the agent toward unexplored regions of the game. The Iris supervisor sends follow-up workers toward the thinnest regions of the Blackboard. Both converge naturally, without a scheduling algorithm, because reducing the highest uncertainty region always produces the largest information gain per unit of compute. The mapping is not metaphorical. The same computational pattern specialize, coordinate through shared state, grow where uncertain, compress where redundant appears in both systems because both systems solve the same type of problem, extracting structured understanding from high-dimensional input under constraints on time, cost, and transparency. This has implications beyond these two systems. Every domain where AI is bottlenecked by cost, scale, or opacity, which is most of them, could benefit from the same structural insight. Financial analysis, where firms process millions of pages of regulatory filings. A 39x cost reduction means the same analysis that cost $50,000 now costs $1,300. That is not a marginal improvement. That changes who can afford the analysis. Insurance, where claims adjusters cross-reference decades of policy documents against individual claims. A stateful swarm that reads once and queries forever eliminates redundant rereading across claims in the same policy family. Scientific research, where systematic literature reviews span thousands of papers. An uncertainty-driven supervisor that targets the highest uncertainty regions of the knowledge base produces systematic coverage that a single-pass approach misses. Due diligence, where acquiring companies review hundreds of contracts in target companies under time pressure. The Iris Swarm API processes the documents, accumulates observations on the Blackboard, and produces typed, provenance-tracked analysis. The attorney reviews the analysis, not the raw documents. When a finding looks wrong, they can trace it back through the provenance chain to the source paragraph. In each case, the naive approach is to use a bigger model with a bigger context window. The structural approach is to decompose, coordinate, and accumulate. The structural approach is cheaper, more reliable, and auditable. And it is available now. The tools exist. The principles are clear. The question is whether the field will build on them or continue to scale the engine while ignoring the road. Intelligence is not scale. It is structure. The free energy principle tells us that intelligent systems minimize. Prediction error by building and testing causal models of their world. Not by memorizing statistical patterns. Not by scaling parameters indefinitely. By actively modeling, predicting, and updating. Active inference turns that principle into engineering. AXIOM turns that engineering into benchmark beating performance with a fraction of the parameters, a fraction of the data, and a fraction of the cost. And the structural insight generalizes far beyond gameplaying. When you need to reason over many long documents quickly and cheaply, legal briefs, financial filings, compliance records, research papers, the same principle applies. Do not throw a bigger model at the problem. Structure the coordination. Accumulate state. Reason causally. Audit transparently. We started 2.5 hours ago with a question: how does a 1.6 million parameter system beat models with 400 times more parameters? The answer is not that AXIOM found a shortcut. The answer is that deep learning is taking the long way around. AXIOM builds the structure that intelligence requires: explicit beliefs, causal models, principled uncertainty, modular specialization. Deep learning tries to approximate that structure through brute force, hoping that with enough parameters and enough data, the right patterns will emerge from gradient descent. One path is efficient. The other is not. The field is at an inflection point. For the first time, systems built on coordination principles are outperforming systems built on scale principles on specific, well-defined benchmarks. The evidence is early. AXIOM's benchmarks are in game environments, not general robotics. IRI's benchmarks are in legal document analysis, not every domain of knowledge work. The technology is young. But the structural insight is general. And the results are real. 400x parameter efficiency. 39x cost reduction. 100% versus 45% on logical reasoning. These are not marginal improvements. They are category shifts. The open questions are genuine. Can active inference scale to continuous real-world environments, robotics, autonomous driving, complex manipulation? The current state of the art is game playing. The path from Atari to a surgical robot is long and full of unsolved problems, high-dimensional continuous state spaces, contact dynamics, safety constraints that cannot be learned through trial and error. The Abu Dhabi Smart City pilots will provide early evidence on whether the principles transfer to traffic coordination and disaster response. But even optimists should expect years of engineering between the current results and general deployment. Can the IRI Swarm API maintain its cost advantage as the document sets grow to tens of thousands of pages and the queries grow more complex? The benchmark data suggests yes. Because the blackboard's accumulated understanding means longer document sets amortize the extraction cost over more queries. The more you query, the cheaper each answer becomes. But the question of how complex the synthesis can get, multi-step legal reasoning, cross-jurisdictional analysis, temporal reasoning across decades of filings, remains open. The architecture is designed for it. The evidence is still accumulating. What is not open is the direction. The deep learning scaling paradigm has produced extraordinary results, but it is running into diminishing returns. Each doubling of parameters produces smaller capability gains at higher costs. The structural coordination approach is producing outsized results at a fraction of the cost. The two approaches are not mutually exclusive. You can use commodity LLMs as components within a structured coordination architecture, which is exactly what the IRI Swarm API does. The question is not which paradigm wins. The question is what sits at the top of the stack, scale or structure. Both systems share one more property. They are inspectable. When AXIOM makes a decision, you can read the beliefs that produced it. You can see which object the SMM detected, which identity code the IMM assigned, which dynamics mode the TMM predicted, and which causal context the RMM used to select that mode. Every step is traceable. When the IRI Swarm API produces an analysis, you can trace it back to the source documents through the provenance chain. You can see which extraction worker produced which observation, which iteration refined it, and which synthesis step combined it with other observations. Every conclusion has a receipt. This auditability is not a feature added on top. It is a consequence of the architecture. When you build a system from explicit causal models and structured state, the system's reasoning is readable by construction. You do not need a separate explainability module. You do not need post hoc attention maps or feature attribution methods. The model tells you what it believes and why. In a world where AI systems are making decisions that affect legal outcomes, financial transactions, medical diagnoses, and public safety, transparency is not optional. An attorney who submits an AI-generated brief to a court is professionally responsible for its accuracy. A financial analyst who uses AI to evaluate a merger target is liable for the conclusions. A physician who relies on AI-assisted diagnosis bears the consequences of a wrong answer. In all of these cases, the ability to trace a conclusion back to its evidence and to identify exactly where the reasoning might have gone wrong is not a luxury. It is a requirement. The structural coordination thesis says you can have transparency, performance, and cost efficiency at the same time. You just have to build the architecture correctly. The future is not bigger models. It is smarter coordination over structured, persistent, auditable state. And it is available now.